Okay, can you guys hear me out there all right? Okay, thank you. Okay, so we'll go ahead and get started where we left off about Newman projections. As you can see on the slide deck here on the screen, we sort of drew this shape here, and this is meant to depict.
12, 30%, 1%, 30%.
You guys have your mic on. Can you mute it, please? So this is meant to depict looking down the axis of a single sigma bond. So again, sort of the front Y shape indicates the three substituents. The fourth substituent, you're looking down the axis. The circle is the rear carbon. And then your substituents of that rear carbon are pointing out from the circle. So what I'd like to start off first is just drawing some Newman projections so we get practice doing that. And this is from your workbook, the first semester topics. This is page 83, chapter 6.1, how to draw Newman projections. So let me know if this is focused okay for you. So maybe just in the chat, yes or no. How many of you have a model kit? Yes or no? So this is a good topic to use that model kit. It's not required formally for the lecture. Perhaps for the laboratory component it is. This type of model kit is called a Darling model. And that's the professor that invented it, Stephen Darling, I believe his name is. So you can see there's tetrahedral carbon. The white indicates hydrogen. Red can be whatever, but so sp3 carbon, 4 bonds, sigma bonds. That's what these model kits are useful for, is this type of activity. So let's go ahead and get started with problem 6.2. We're given this molecule here, which I would, when I look at that, I would name that 2,2,3,3 tetramethylbutane. So let me throw some numbers in there so we're all on the same page. So here's carbon 1, carbon 2, carbon 3, carbon 4. So it's asking us what this arrow means. That's your eyeball. And your eyeball is looking down the C2, C3 bond. That is important, that order, 2 to 3. That's your perspective when you're answering this question. So we want to look down this sigma bond axis and then put these substituents. So this is the front carbon right here. So that little dot here, that's carbon 2. So you have your substituents coming off it. Then carbon 3 is in the back. So looking down the C2, C3 bond, this one's sort of straightforward. What should all of these substituents be? Maybe in the chat you can type your answer. So they should all be methyl. because you have methyl, 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 methyl. So maybe for the carbon 2 in blue, I'll write methyl. Then carbon 3 in red, I'll write methyl. So again, just as a review, you may think this molecule is selfish because it's me, 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 me. But what does that mean in organic chemistry? So methyl is, remember, CH3. So that's what Me means. That's what we communicate by methyl. So on carbon 2, which are the substituents coming off, you have methyl, 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 and that's what we've drawn. Methyl, 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 methyl. Now, the next thing I want to ask is, do you all understand, maybe I'll circle it in purple, that this methyl group here that I just circled, see how it's coming down when you're looking at it? That methyl group is this right here. Then see this one that's projected towards you? This methyl group is that one right there. And then the one projected away from you, that's what the dashed line means, is this one. Let's go ahead and we'll do 6.3, and then that concept should be a little bit clearer about why things go where. So maybe what I can do is the following. Again, when I look at this 6.3, I say this is 1, 2, 3, 4, so that's a butane derivative. So Hannah, well, I think by doing this, we'll sort of answer your question. So I'm just going to use numbers here. 1, 2, 3, 4. I'm going to show you just the name. So it's 2,3 dimethyl butane. So we're still practicing our skill we've developed. We are looking down the C2C3 bond. So maybe in purple, on carbon 2, I'm just going to put numbers 1, 2, 3. Now in the chat, what I want you to write is 1 equals, 2 equals, 3 equals, and tell me what the substituents at 1, 2, and 3 should be when you're looking down that axis. Again, we're considering the stuff bonded to carbon 2, that's carbon 2. What should go where on 1, 2, and 3 based on looking down that axis? So Hannah says 1 equals hydrogen. Yes, that's correct. 1 is the hydrogen. So I'm just going to cheat here a little bit. So because you're looking at, your sort of eye is in the plane, this is out, so it's to your right. So 1 equals H, 2 equals methyl, 3 equals methyls. Yeah, so this right here pointing down is this. So that's equal to methyl. Then this pointing away from you is 3, so that also is equal to methyl. So what about 4, 5, and 6? Now those are the things bonded to carbon 3. So what should they be? 4, 5, and 6, based on that perspective. So 4 equals methyl. Five equals, we have some disagreement here. Hannah and Aiden both say 5 equals H. Max says it should be methyl. I'm going to agree with Mac in that 5 is equal to methyl, and then 6 is equal to H. And I'm going to show you why I agree with Mac. So we said position 1. See how we said it's H? Now look at, see how this is a wedge, it's coming out towards you. This wedge, this methyl here is coming out towards you. These are close to one another, right? So in the Newman projection, they also have to be close to one another. So H methyl. So see back here, we said 3 was this methyl. So this 6 has to be this H, because that dash is going away, that H is going away. So they have to be close to one another. Is that clear to everyone? So really, maybe this will help you think about this. Again, my teaching philosophy is I don't believe I have to teach exactly how the book presents it. The book is one source of information. I'm another source of information. So it's sort of like watching news channels. There are multiple news channels for different points of view. And so sort of to get what Hannah is pointing out about left and right and up and down, what this exercise will help you with in terms of a skill set is how you visualize things if you don't have a model kit. If you do have a model kit, then that's great. But if not, this will help you to do that. So let me, and there is a screencast in Canvas about this, but let me sort of get to what Hannah is asking about left, right, up, down. So I got some fancy highlighters here. Let's look at 6.4. And to get to Hannah's first, maybe third thing in the chat there, let me explain the up, down, and then I'll do the left, right. Or okay, I'll do it on this one. Okay, so let's recall that when we have just a regular bond like this, see this backbone? That's the butane backbone, right? As we've drawn it, it is in the plane of this paper. Your eyeball is looking at this orthogonal to the plane of the paper, right? And that's why we draw it this way. See this bond, this wedge, in this wedge? They are projected out towards you. The dashes are projected away from you. So you're looking orthogonal and you see this backbone, right? I just highlighted in pink. Now, if you imagine your eyeball looking straight down, what this arrow is telling you is your eyeball now has to rotate 90 degrees to be in the plane of this paper. So now that 4-carbon backbone, see how this group is down and that's down? The 4-carbon backbone is now this straight line that I've highlighted. You have carbon 1, carbon 2, carbon 3 behind, and carbon 4. These purple numbers I just used as a pedagogical tool to discriminate between left, right, up, and down. They don't have anything to do with this green numbering. And again, the reason I'm sort of using different colors is to highlight different things. So this backbone is in the plane of the paper when you're looking at it orthogonal. When you're looking at the Newman projection, you see it in a single axis here. So this carbon's down, it's there. This carbon is up, it's there. So when your eyeball is in the plane, this H is projected to your right, and the methyl is projected to your left. Maybe let's review that on 6.4 here. So with my pink highlighter, and again, you know, I never really used a whole lot of color prior to COVID, but since COVID happened, you know, in trying to teach and help students understand things better, I think the use of color, I bought a shitload of different types of pens, as you can see. The color helps me, I think, help students explain different concepts rather than just writing all in say, black. So with the pink highlighter, I'm highlighting the longest carbon backbone. So I've highlighted that. Then when I look at this Newman projection, it's asking us to look down that axis. So if I highlight that in the Newman projection, it's now here. So if you're looking down this, you're looking down that sigma bond axis. What should go right here at the bottom? So Lexi and Mac are both saying different groups. So maybe we can get some consensus about which group is the most appropriate. So again, this is the front carbon. I'm circling that in blue. Circled it in blue. That's that front carbon. You're looking specifically down that axis now. So what group should go here? Just waiting for a couple more people to respond before I write something down. Again, because it's really your opportunity to either ask a question or present an answer so that you understand it. So yeah, it's ethyl, right? So coming off the bottom is CH2CH3. We can just abbreviate that ethyl. And then what goes here? So H. And then that's the H projected that way. The H projected behind is here. So now when you're looking down this axis, what goes on top? So that's the methyl group, CH3. These things are the same, so they're both H's. So let me just point out some more terminology that you'll see. When you're looking down this bond, the way this is drawn, the longest chain, all these substituents are staggered. So there's no sort of bond overlap. So staggered. And then the relationship between the methyl and the ethyl group, we call that anti. which means that they're 180 degrees apart from one another. So really, you can do that for any two substituents. So what do I mean by that? So say this angle here between the methyl and H, that's a 60-degree angle. This is 60, that's 60. So overall, 3 times 60 is 180. So that we do something a little bit different looking, let's do 6.7. Because this one is different now. So I'm going to highlight the carbon backbone that is in the plane of the paper. So I highlighted that. The blue carbon is out front. So based on that, what should go, we're only dealing with the front carbon. What should go right here? So that's methyl. Then what goes down? So this is methyl. And then finally, the last substituent that goes here. So this is H. Notice how now the reverse carbon, see this, all this space between those substituents, that angle 60 degrees. This is no longer staggered. We call this eclipsed now. That means sort of the angle between the front and back substituent is 0 degrees. So now we're looking at the back carbon. So what should we put here on the back? Keep in mind, see this wedge is out, that H is out. So what should go here? I think people have responded H. Now look, this group was down. What group goes in the back here? So methyl. And then finally, the last group, this H was back, it's to the left. So this H has to be back and to the left. So this is called the staggered conformation. This is called an eclipsed conformation. Are we pretty good on doing this skill or task, activity, etc., from converting from one perspective to another? If you have concerns or questions, unmute or put them in the chat. So I'd like to just show why this is a useful activity. Or what it is used for. So let's just consider ethane. CH3, CH3. It's an alkane, A and E. We have a sigma bond. So I've put in quotations free rotation about a sigma bond. So that's typically sort of a colloquialism that we use. But based on this analysis, the rotation really isn't free. And what I mean by that, there is an energy penalty that you have to pay to do that rotation. And this is where the Newman projection comes in handy. Since there's only one sigma bond, we're going to look down the only sigma bond in ethane. So I'm going to start with the staggered conformation. And what I'm going to do, just so that we see something is happening, because all the substituents are the same, they're all hydrogen, right? I'm just going to use blue and red to show that something is actually happening in this process. So I'm going to mark one of the front hydrogens red and one of the rear ones blue, and the rest of them is black. And so what I want to do is rotate about that axis. So I have an arrow with a little curly Q there. That just means we're rotating about the bond, and we're going to do a 60-degree rotation. So maybe I really can't get this document camera to get everything in sort of the frame. But here's the flat drawing. Here's sort of the model that we can so we're looking down the carbon-carbon axis. There's a red hydrogen, there's a blue. So what I'm going to do is I'm going to take this and see how now it's staggered. I'm going to rotate 60 degrees, watch the red move over, and it's going to eclipse now this hydrogen, because I'm going to do a clockwise rotation. So now it's sort of blocking the rear hydrogen, right? So it's eclipsed. So let's go ahead and draw that. So the back substituents are staying the same. So let me just keep those the same, so you see I'm not pulling any tricks on you. I just put those in, they're staying the same. We're rotating this way. Whoop. It should be red. So it's kind of hard to draw the eclipse because they overlap, obviously. So staggered, eclipsed. So when that happens, these things are sort of, they're, even though the model doesn't look like it because they look like they're far apart, right? Like these hydrogens look like they're far apart. Again, this isn't the most accurate description of ethane there is. Remember, there's van der Waal, the radii, where this takes up space, this takes up space. So these things are actually banging into one another. So you have that. You have this other pair, and then you have this other pair. So you have three of those eclipsing interactions. You have 1, 2, 3. So overall, the energy penalty for doing this is plus 12 kilojoules per mole. So it takes 12 kilojoules per mole to do that, what we're saying, free rotation. If we take 12 divided by 1, 2, 3, each of those gives a +4 kilojoule per mole energy penalty. So to rotate from staggered to the eclipse, you have to put energy into the system. Energy is typically heat, right? So this is relatively, in terms of the scale, we'll draw this out. This is an energy of 0. Now this is 12 kilojoules per mole higher in energy. Then if we rotate again, we're now staggered. So let's draw that. So we trace this red. So let me draw the back carbon atom first, so we can see that that one is, we're holding that one still, we're not moving it. So now we're H, H, and then red is here. So again, I'm using the red and the blue to show you that the movement is actually happening. Because if I was just using black, they would all look the same and you wouldn't see, it wouldn't perceive to you that anything's changing. So the relationship between the red and the blue, that's anti, because it's 180 here. Now we're eclipsed. Now this has a special name here. If we're considering these two substituents that are 60 degrees apart from one another, this relationship is called Gauche. So 60 degrees, G-A-U-C-H-E. So again, this is staggered. Staggered, eclipse, staggered. So as you do this sort of exercise, you'll see that it goes from staggered to eclipse to staggered. That's how they vary. So what I want to show you now on the screen is a rotational plot that I put up in Canvas as well, and we'll plot this data. Any questions on what we were doing here before I throw down the plot page? So here's our sheet. Analysis of conformers by relative energy versus dihedral angle rotational plot. Again, I would, you can print these out. It's on Canvas. Do it for pretty much any molecule. What's the molecule name? Ethane. We're looking down only C1, C2. That's all we can look down. Here's the energy penalties for those eclipsing interactions. So the sheet is in the page that says lecture screencasts. So if you scroll down that, it might be a bit hidden, but it's as a PDF file. So these are all eclipsing, eclipsing. There's a gauche. We'll look at where you find that, and then they're eclipsing. So each HH eclipsing, there's 4 kilojoules per mole energy penalty. So let's go ahead and we're going to plot the dihedral angle versus the energy penalty. So we said the first thing we're going to draw in this box here is the staggered conformation. So we said at staggered, again, the important thing to realize is this word here, relative. So we're saying for this one, the relative energy is 0. And so our dihedral angle, we're starting at 0 here. So basically, we're going to put a point. So at dihedral angle of 0, the relative energy is 0. So there's our data point. Now we're going to do a 60-degree rotation, and we find that we go from staggered to eclipsed. So we have H, 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 and then the blue H is at the bottom here. The red H is to the right. So we have 1, 2, 3. I'm missing an H there. So we have 1, 2, 3. 3 HH eclipsing interactions. Each has a penalty of 4 kilojoules per mole, so that's 12. So we did a 60-degree rotation now. Here's 10. So we're estimating this data point about there. Let's go ahead and do another rotation. So we're back to, we have H, 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 H. Our blue H is always at the bottom. We're keeping that as our sort of constant. The red H is here now. This is completely staggered. We have no eclipsing interactions, so that's now sort of the same as the first one. So we have a data point here at 0. So these are sort of this first and third one are the same. So that's how we put the relative energy is 0. So now we have 3 data points. We can draw a curve. What does this curve mean? So in terms of this model here, so here's this Newman projection. I've just made the model. That Newman projection is sitting at this point on the curve. And so, you know, if I was a Hollywood movie maker, I could make a fancy animation about how this happens. But since I'm not, I have this plastic model here, which I can't really get completely into the frame for it to look correct. Okay, so there we go. There you see the completely staggered. As this moves up this hill, this energy penalty, the bond is rotating, and watch the red atom, red hydrogen move closer to impinging the rear one. So as this twists, that's the energy going up till you get to the fully eclipsed. Then you're sitting at the top of that hill. That's your energy penalty, meaning this conformer is less stable than the one where it's staggered. So as the bond continues to rotate, you're going down the curve. Then you're back to the staggered conformation. So what does this curve mean? As the bond is rotating, that's when you're encountering these eclipsing interactions. So here we're stable, and as we move up, you're rotating to eclipsed. So because you only have the same energy penalty no matter what you do, this curve is just like a sine curve, right? Is that clear? So Carly says kind of. Again, the reason this is important is that, and why I understand why organic chemistry is difficult to really, you know, connect all these concepts, is that this model, this ink on this paper is a static image, but in reality, this bond rotates in an ethane molecule a crazy amount of times per second, millions, if not billions of times per second. So there's enough energy at room temperature for this to spin really fast, but it does create a penalty. There has to be heat put into the system to get over that barrier. So keep in mind, even though we're dealing with static things, they're always in motion. So what I would like to do is now go one up, and let's look at propane. So you can see that the curves do not always look the same. There's different interactions at play. So here's propane. We're gonna look down, say the 2,3 carbon 2 carbon 3 bond. So if I do that, we're looking down 2,3. The thing going down, that'll be our methyl group. So I'll put that methyl group in red. We're going to keep the back carbon the same. The back carbon is here. 1, 2, 3 hydrogens. These are all hydrogen. I'm gonna write one of them blue. Hydrogen, hydrogen. Then the other two things on carbon 2 are hydrogen. So this conformation is staggered. What we are going to do, again, is a 60-degree rotation. Let's just go clockwise. I think that's the easiest thing to do when you're doing these type of problems. Just keep the back one constant. Move the front one. Always do the rotations clockwise. So the curves don't really have like sine or cosine. I guess unless it looks specifically like that. But this one's going to look a little bit different because you have a separate energy penalty. So when we do that, so H, we're going from eclipsed to staggered. Or sorry, staggered to eclipsed. So it's always a little bit hard to draw the eclipse because you can't draw exactly on top of one another. But the methyl, the H, this whole energy penalty costs now 14 kilojoules per mole. So to do this rotation, it costs 14. We already said that HH eclipsing was +4. This is +4. So what does that make this remaining penalty? So yeah, we have 4 + 4 is 8. 14 - 8. This is +6. So we can do another rotation to get back to the staggered. So we have H, 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 H. The methyl now is here. So now we're saying there's no energy penalty for this. So 1 and 3, the first and third conformations are virtually the same. When you go through the rotation, you're adding 14 +4 for the HH +6 for the methyl H. So if we were to plot this, it would actually sort of look the same as the ethane because you're only going from 0 to 14. So it's going to go 0, 14, 0, 14, 0, 14, infinity. So that one won't look terribly different in terms of like the shape of the curve, just the energy penalty changes. So maybe I can show you that on a pre-drawn sheet. So this is the conformational analysis of propane. There's our dihedral angle. We're staggered. We rotate. We get to eclipsed. Now we're at 14. We're going back down to staggered. So the relative energy goes back to 0. So it just sort of repeats the same. It's just a little higher. Any questions before we do? We're going to do butane, and we're going to see that the plot for butane is different because the bond that we look down is going to have a new interaction. So maybe I'll just draw this right on the rotational plot here so we're not repeating things too much. Molecule name is butane. There's the structure of butane. Let's look down C2, C3. So our eyeball is looking down carbon 2, carbon 3. So this group is down. I'm going to call that methyl. That group back there is up. I'm going to call that methyl. Just we're going to keep the back carbon constant. And then everything else is hydrogen. We're going to do a clockwise 60-degree rotation of the front carbon. Let me just keep the back stuff constant. So we haven't done anything with the back carbon. Now we're going to have from staggered to eclipsing. So the red methyl group moves over. Now we have a methyl H eclipsing. We said H methyl eclipsing, that was worth +6. We put in our remaining hydrogens. So we said our penalties here, we're looking for eclipsing interactions, plus 6, H-methyl plus 6, HH plus 4, 6 plus 4 is 10, plus 6 is 16. So let's start plotting that. For our staggered, we were at 0. When we rotated, we're at 16. Now let's rotate again, another 60 degrees. Again, these are always 60-degree rotations. I'm going to put the back stuff in. Now again, we're staggered, so the bonds go in between. So this actually does have a new energy penalty, even though they're not eclipsing. These two methyl groups are close to one another. So this is called the Gauche interaction. The methyl-methyl Gauche interaction has a penalty equal to plus 3.8 kilojoules per mole. There's no other energy penalties associated with that, but due to the steric effects, and steric means like space, the space of that methyl group impinges on the space of that methyl group. So we go over for this, here's 5, we're at 3.8. So now we put a data point there. We'll draw the line in after we do a couple more rotations. So we're going to do another 60-degree rotation, and what you'll find now is we have a new interaction, methyl-methyl eclipsing. So the two methyl groups are now eclipsing one another. The hydrogens are eclipsing. We already know HH eclipsing is plus 4, plus 4, plus 4. Now, since methyl groups are bigger than H eclipsing, they have a significantly higher energy penalty, and so they're equal to 11. So methyl-methyl eclipsing is plus 11. 11 plus 4 is 15, plus 4 is 19. So for this conformer, there's 20. We're now significantly higher. So if we continue our rotation through, we're back to staggered. But you see, once we go through that, the methyl is over here now. These two are gauche again, so that's plus 3.8. So now for this, we're back down. We're sort of even with this gauche interaction. So you can see that this curve is going to look different as we connect to these points. So notice this doesn't dip all the way to 0 as you go through the rotations. So again, how do you interpret this? Again, you're comparing these conformers in the relative energies to each other. So when the methyl-methyls are anti, that's the lowest energy conformer, and we assign that to 0. as you start rotating and you get these eclipsing interactions, you evaluate them according to their energy penalty. The most recent one, so let me just put these in. So here's 0. What did we say? This one was plus 16. This was plus 3.8. This was plus 19. And then this was plus 3.8. You can continue on graphing this. But what this is telling you, so when you look at sort of these points, you know, you can draw these lines and look at energy differences and say, okay, between this eclipsed and that eclipsed, that one's 3 kilojoules per mole energy higher than this one due to this interaction specifically. Or, you know, if you're looking at sort of from the baseline 0 to 3.8, you're paying that energy penalty for the Gauche interaction. So again, this sheet is posted in the lecture. The lecture page of module 3. There's also a lot of screencasts on nomenclature, conformational analysis that you should review as well. Since we're almost out of time, I'll leave the last couple minutes. Do you guys have questions that you want to answer before our time is up for today? Again, your workbooks are really good for practicing this stuff. The model kits are really helpful as well because they can help you visualize, because I know it can be hard when you're learning this stuff to do these rotations in your mind. So what I typically do is I take like the colored red or blue and I make them like, I can say, okay, this is a methyl, this is a methyl. Then I'm looking at, you know, butane itself. Aiden asks, what is the significance of conformers in terms of interactions with other molecules? So Aiden's asking about the reason this is important is because we build upon it when we learn reactions. When we start learning, when two reactants collide, remember in a reaction, things have to collide for a reaction to occur. So they collide, a bond is formed. The reason conformational analysis is important is because some of these conformations are more reactive than others. The reactivity does not necessarily mean something, the highest sort of point on a curve here. So we have to learn how to evaluate this activity first. Then we can diagnose other parts of a conformation to say, okay, this reactant will only react with one of these conformations. And that has a lot to do with the steric effects I was talking about, the space at which functional groups occupy. So Hannah asked about a specific molecule here. Can you show 3-ethyl 2,2,4,4 tetramethyl pentane? So this is a nice skill to develop. How would I go about doing this? First, I would draw pentane. 1, 2, 3, 4, 5. And I might throw some numbers in there to help me out. 1, 2, 3, 4, 5. There's our pentane. 3 ethyl, so 1, 2, 3. There's the 3 carbon, and ethyl group is 2. 2, 2 has methyl, 4, 4. So there is 3 ethyl 2, 2, 4, 4 tetramethyl pentane. Hannah, was there a specific other question you were asking for, or just the structure of that name? Looking down the three carbon towards what though? Maybe if you want to unmute and ask a question so I can understand what you're trying to get at exactly.
Oh, it was in the book. It was Skill Builder 4.7, and it showed the drawing, but that was the name of it. And it was looking down, not the 3, but the carbon below 3, off of the ethyl.
This is in the textbook, correct?
Yes, it's in the online textbook. It's under section 4.7, drawing Newman projections, and then it's Skill Builder 4.7.
Okay, yeah, so they're looking down. So they're drawing it in the book this way specifically. So they're drawing it that way, and they're telling you to look down this bond. So, so this is your front carbon atom. Whenever I see that going down, the way that I start to draw the Newman projection is, okay, there's the down bond. Then I'm going to draw sort of the Y this way. So that's the front carbon atom. That methyl group is down. We have 2 substituents, HH. Then we have the rear carbon. Now see how we're looking down this bond. This is the rear carbon. See how this group is up? That entire group has to be anti to this methyl, so that group goes up. So that is this group. They're saying that this is a wedge, which means the hydrogen is a dash then. So that is projected out towards you, so it should be over here. And then the H should be to the left. Does that help in terms of answering that question? Okay, well, I'm gonna go ahead and stop the recording of this. Again,